Question number 76. A simply supported beam of circular cross section with diameter small d and length L carries a concentrated load W at the center of the beam. The strength of the beam is proportional to simply supported beam with central point load W. The total length of the beam is L and the diameter of the beam, that is circular in section, is small d. Okay, so maximum bending moment at the center M will be WL by 4, and the section modulus for the circular section Z will be pi d cube by 32. Now we know the relation M equal to sigma into Z. Sigma is the bending stress, Z is the section modulus from the section, and M is the bending moment. M proportional to Z and M is equal to WL by 4 proportional to Z means pi d cube by 32. So we can write W proportional to d cube by L. Here W is the maximum load that the beam can carry, which is the actual strength of the beam, which is proportional to the d cube by L. And B is right answer. Number 77. A cantilever beam carries a uniformly distributed load from fixed end to the center of the beam in the first case, and a uniformly distributed load of same intensity from center of the beam to the free end in the second case. The ratio of deflections in the two cases is cantilever beam of total length L. In first case, a uniformly distributed load W per unit length is from fixed end of the cantilever beam to the center of the beam. Okay. So under this condition, the deflection at the free end B will be 7WL to the power 4 by 384 EI. That is equation number 1. And in the second case, the beam is same and the load intensity is same, but the load is from center of the beam to the free end. So the deflection at the free end under this load will be 41WL to the power 4 by 384 EI. That is equation number 2. So if we make ratio del B1 by del B2, the ratio will be 7 by 41. Option D is right answer. Question number 78. If the length of a simply supported beam carrying a concentrated load at the center is doubled, then the deflection at the center will become a simply supported beam AB, total length L, and subjected to a central point load P. So the deflection at the center, that is maximum, will be PLQ by 48 EI. Okay. So from this relation we can write del C, or the deflection at the center, is proportional to the L cube of the beam. L is the length of the beam. Okay. Now if the length of the beam is doubled, then the deflection at the center will be 2L cube. So del C will be 8L cube. That means 8 times. Deflection will be 8 times than before. Option C is right answer. Question number 79. A simply supported beam with rectangular cross section is subjected to a central concentrated load. If the width and depth of the beam are doubled, then the deflection at the center of the beam will be reduced to the simply supported beam AB of length L subjected to a central point load P with rectangular cross section small b width and small d is the depth. The central deflection del C will be PL cube by 48 EI. We know that relation. And for this section with B and depth small d, the moment of inertia I will be BD cube by 12. And from this relation del C equal to PL cube by 48 EI, we can write del C proportional to 1 by BD cube. That is equation number 1. But when the width of the beam is doubled and depth of the beam is also doubled, the deflection at the center will be 1/16 into BD. Now if we find out the percentage of reduction in deflection, that will be equal to the del C1, that is deflection after the dimension is changed, divided by the original deflection into 100%. And if we put all the values, then we will get the percentage equal to 6.25%. Option D is right answer. 80. A laminated spring is given an initial curvature because spring becomes flat when it is subjected to design load. Option C is right answer. Question number 81. A laminated spring is supported at the ends and loaded at the center. Option A is right answer. Question number 82. Laminated springs are subjected to bending stress. Option B is right answer. Question number 83. Deflection in a leaf spring is more if its stiffness is less. Option C is right answer. higher the deflection stiffness is less and lower the deflection stiffness is more. Deflection is inversely proportional to the stiffness of the spring. Option C is right answer. Question number 84. A carriage spring of span L consists of n plates each of thickness small t and width small b. If the spring carries a load of W and modulus of elasticity of spring is capital E, then the central deflection of the spring is. Option A is right answer. Question number 85. Buckling load for a given column depends upon both length and least lateral dimension. Option C is right answer. Question number 86. When both ends of a column are fixed, then the crippling load is P. If one end of the column is made free, the value of crippling load will be changed to, we know the Euler's buckling load formula, P equal to pi square EI by L square. E is the modulus of elasticity of the column material, I is the moment of inertia of the column section, and L is the effective length of the column. But as per question, when both ends of the column is fixed, the effective length L will be L by 2, the original length by 2. So the buckling load P will be 4 pi square EI by L square. Okay, but when one end is fixed and one end is free, the effective length will be 2 times 2L. Then the buckling load P2 will be pi square EI by 4L square. Now if we multiply this value with 1 by 16, then we can write P2 equal to 4 pi square EI by L square into 1 by 16. And we know this value is equal to P, so we can write easily P2 equal to P by 16. A is right answer. Question number 87. Euler's formula for a mild steel long column hinged at both ends is not valid for slenderness ratio. We know the formula for Euler's buckling load, P equal to pi square EI by L square. E is the Young modulus of the column material, and I is the moment of inertia of the column section, and LE is the effective length of the column. Okay, and we also know the relation I equal to AK square. I is the moment of inertia of the column section, and A is the area of the section, and K is the radius of gyration of the section. We know the formula for slenderness ratio, lambda equal to L effective by K. So by putting the value of I equal to AK square in this equation, we can write P equal to pi square EAK square by L square, and buckling stress value is equal to P by A. So we can also write sigma equal to pi square E by lambda square, that is slenderness ratio. So slenderness ratio lambda will be equal to pi into root over of E by sigma, and E is the modulus of elasticity of the column material, and column is made of mild steel, so E value will be 2.8 into 10 to the power 5 Newton per millimeter square, and this sigma buckling stress value for column material will be 300 Newton per millimeter square. So after putting all the value in this equation, lambda will be equal to 83.1, which is less than 80. If the slenderness ratio is less than 80, Euler's formula will not be valid for MS column. And B is right answer. 88. A long column has maximum crippling load when its both ends are fixed. Option B is right answer. We know the formula for Euler's buckling load, P equal to pi square EI by L square. E is the modulus of elasticity of the column material, I is the moment of inertia of the column section, and LE is the effective length of the column. Okay, but when both ends of the columns are fixed, then effective length will become L by 2, half of the original length. Then the buckling load value will be 4 pi square EI by L square, that is the 4 times the previous load. Question number 89. Effective length of a chimney of 20 meter height is taken as. Chimney is like cantilever column, one end is fixed and other end is free, so L effective will be 2 times the original length of the column. So the original length of the chimney is 20 meters, so effective length of the chimney is 40 meters. Option D is right answer. Question number 90. Rankin's formula for column is valid when slenderness ratio has any value. Option D is right answer. Number 91. Slenderness ratio of a 5 meter long column hinged at the both ends and having a circular cross section with diameter 160 mm is. We know the formula I equal to AK square. I is the moment of inertia of the column section, and A is the area of the section, and K is the radius of gyration of the section. For a 5 meter long column circular in section, the Moment of inertia of the section will be pi d to the power 4 by 64, where d is the diameter of the circular section and a is the area of the circular section. So area will be pi d square by 4. So k will be equal to root I by a. That means, and if we calculate, k will be equal to small d by 4. Small d value is given in question, that is equal to 160 mm. So k will be equal to 40 mm. And we also know the formula for slenderness ratio. Lambda is equal to L effective by least radius of gyration k. So we know the both value. Effective length is equal to 5000 millimeter length of the column, and the least radius of gyration k is equal to 40 mm. So if we put the value in this equation and calculate, the slenderness ratio of the column will be 125. D is right answer. Number 92. Effective length of a column fixed at one end and hinged at the other end is L by root 2. Option B is right answer, where L is the actual length of the column. Question number 93. The effect of arching a beam is to reduce the bending moment throughout. Option A is right answer. Question number 94. Internal forces at every cross section in a arch are normal thrust, shear force and bending moment. Option D is right answer. Number 95. According to Eddy's theorem, the vertical intercept between the linear arch and the center line of the actual arch at any point represents to some scale the bending moment. Option A is right answer. Question number 96. Due to rise in temperature in a three-hinged arch, induced stress is. A three-hinged arch is statically determinate and can freely expand or contract when the temperature changes. Therefore, a rise in temperature does not produce any thermal stress in the arch. So, induced stress will be equal to zero stress. And D is right answer. Number 97. In a three-hinged arch, the linear and actual arch meet at least 3 points. Option A is right answer. And the 3 points are two ends and the crown at the middle. Number 98. If a three-hinged parabolic arch carries a uniformly distributed load over the entire span, then any section of the arch is subjected to. Any section of a three-hinged parabolic arch is subjected to normal thrust and radial shear and zero bending moment. So option B is right answer. Number 99. Three-hinged arch is statically determinate. Option C is right answer. Three-hinged arch A, B, C. Hinge at A, hinge at B, and hinge at the crown of the arch at C. Now we will get two reaction from this hinge end at A. One is horizontal reaction and another is vertical reaction, and two reaction component from this end, that is B. So 2 plus 2 equal to 4. Now we know the formula for degree of static indeterminacy. ds is equal to r minus 3 minus small n minus 1. Small n is the number of member connected to the hinges, so that will be equal to 2, because for these hinges at C, two members, that is AC and CB, is connected at here at the crown, so n value will be equal to 2. So after putting all the value, reaction components will be 2 plus 2 equal to 4. So 4 minus 3 minus 2 minus 1. So ds value will be equal to 0. Question number 100. If the central rise of a symmetrical parabolic arch is h, then the rise of arch at the quarter point is. So three hinge parabolic arch A, B, C. One hinge at A, another hinge at B, and third hinge at C at the crown of the arch. Okay, and total length of the arch is small l. As this is a parabolic arch, the height at any section y will be equal to 4hx by l square into l minus x. And if we want to find out the rise of arch at the quarter point, that means x equal to L by 4 from the A at quarter point means. Okay, so if we put the value of x equal to L by 4 in this equation, y will be equal to 3h by 4. Option D is right answer.